So I apologize profusely. One of those mornings. So sorry, we're starting late. All right, last time we talked about Fourier series, and then I briefly mentioned that you can move those series into the Fourier transform. So the Fourier transform looks very similar to the Laplace in that it has a frequency domain equivalent to it. So for like delta function, it goes over to 1. 1 goes to pi delta, or the direct, and then so on. So with the Laplace, we were doing everything was u of t, meaning that it didn't start till a specific after 0 time frame. So that's now where this is different, in that we have functions that can be, continuous forever in the negative and the positive. So how do we use this? We're going to move into this example. I did upload these notes. They're lecture 19, Fourier. Are you guys hearing me okay online? Okay, great. All right, so if we get this circuit here and we want to solve this in the Laplace, the first input signal has a u of t, the second signal has u of t, but the third one does not, which means we can't use Laplace for that third signal. So to solve this, take a minute to write an equation to solve for IC of t. For Laplace, you're going to replace the capacitor with 1 over SC. And for Fourier, you are going to replace it with 1 over j omega c. Yep, 1 over j omega c. So go ahead and write an equation. Take a second to write an equation for IC in terms of both of these, Laplace and Fourier. And for the Laplace, because we are doing u of t at t equals 0 minus, you're going to have a VC of 0 minus will be 0. Yeah. Four K times 0.25 milli goes to 1. Uh-huh. Yes. Voltage source. Haven't written that out yet. I just did in terms of VS. So when I plug in the VS is 10 over S, then the S's will cancel. So a question online was if you know, for the Laplace, if we have VC of 0 minus is not 0, and we actually have initial value, what would be the difference? And so if it's not 0, they're going to add in voltage source of VC 0 minus over S, and then you would solve IC from that. So hopefully you guys have been able to get that IC would equal VS times 5 times 10 to the minus 4th over 3 plus S. Okay. So equation, this current is going to be VC minus VS over 2K. This current is VX over 4K. And this current is VX over 1 over SC. And then IC will be VX over 1 over SC, which can also be written as VX times SC. So I combine all of the same variables. So 1 over 2K plus 1 over 4K plus SC. And then I take the VS over 2K over to the other side. And then combining those, I take 2 over 2 or 2 over 2 over 2K becomes 2 over 4K. SC becomes 4K over 4K. And then that becomes 3 plus 4K SC over 4K. That 4K goes to the top. And then 4K times 0.25 milli is equal to 1. So this term then becomes 3 plus S. And then 4K divided by 2K is 2. So that gives me the 2 on top. And then I just multiply that VX times SC for IC. And then 2 times 0.25 milli becomes 5 times 10 to the minus 4th. And I'm yes. Thank you. Yep. So 5 times 10 to the minus 4th S over 3 plus S. All right, now you got. Yeah. So yes, S should be there. Take a minute to figure out if you didn't get that, what you did. Yes. So only if you had an S times 3 plus S could the S's cancel. All right. Yes, you guys got this. No, you did not get this. Yes. So if that S on the top canceled, you would be able to just do 5 times 10 to the minus 4th e to the minus 3t. U of t would be your time domain. Yep. It makes it very easy. Well, times VS, so you still have to see what VS input signal is. All right, any questions about getting this? Okay, so this is the Laplace that we've done before. Now we would want to plug in VS. So if we look at the first input signal, the Laplace of 10 U of t, what was that? 10 over S. So now we will plug that in. And we would get IC is going to be 10 over S times 5 times 10 to the minus 4th S plus 3. So here they do cancel. And we can just write IC of t. What is it 5 milli? Let's see, 5 times 10 times 10. Yeah, 5 milli. E to the minus 3t U of t. So this would be our solution for the Laplace. Now Fourier is going to be the same equation set. The only difference will be that S, instead of S, it will be j omega. So my IC for the Fourier is going to just look like VS so this will be my equation for IC. And now we take the Fourier transform of 10 U of t. So that's going to be 10 pi delta omega plus 10 over j omega. And then we plug that into the VS. And then we can go backwards. So for the first term, it is not in the table because we have a delta W j omega over j omega plus 3. So the Fourier transform is 1 over pi. And then you take the function and then multiply it by e omega t, and then you do it over dw. The second one over j omega plus 3 is going to be this transform. So it just becomes 5 times 10 to the minus 3 e to the minus 3t u of t. As we integrate this delta function, we only get an integration at one point, and that ends up going to 0 for that term. And so we end up with 5 times 10 to the minus 3 e to the minus 3t u of t, which is the same. Uh-huh. Correct. So, so that's the definition of the Fourier. So the Fourier transform. They are in the ULB book. So, oh, lost it. So they're in the ULB book on page 722. And just like with the Laplace transform, you also have the properties of the Fourier transform. So when you have E multiplied through the minus j omega t naught in the frequency domain, it shifts it in the time domain. So these are very similar to the Laplace ones, except for they're for the Fourier. So if you, grab it here. So these are just very similar to what we saw for the Laplace. And the book goes through the derivations if you have interest in those. But when you have a constant in the frequency domain, you're going to have a constant in the time domain. So that is the same, function. If you are adding in the frequency domain, you're going to add them in the time domain, or vice versa. If you have an addition in the time, they just add in the frequency. If you have a times t, then it becomes 1 over a, or the magnitude of a, f of omega over a. So these were just the same as the Laplace ones, except for now, instead of s in there, it's j omega or omega. So these are the most common ones. And so those properties are going to be similar. From this, you see that, okay, I can, get the same exact result as the Laplace. The Laplace is just a little bit easier mathematically. Or hopefully that's what it seems like to you. Questions on how this is done? Yes. IC of t, or what do you mean IC?
You solve for Vx, right?
Uh-huh. Yep, I just plugged in Vx and then multiplied it by SC.
So then I would just, for the Fourier transform, substituting what that has to be for j omega.
Yeah, but I mean, you can go through the whole derivation again, except the only difference will be instead of here being 1 over SC, it's going to be 1 over j omega c.
So this is just like 2 ways to go about solving the same problem.
Yep. Yep, they're just 2 different methods to solve the same problem. One is using Laplace and one is using Fourier.
So what would be the direct benefit of using Fourier over?
We're gonna see that when we get to number C. Because for C, we can't use Laplace at all because we don't have a U of T function in there. So we can't determine what the initial conditions are. So because we can't use that, we want to know, like, how do we solve that? And so we would have to use Fourier. So that's the benefit, is that Fourier allows us to solve for any circuit, or any circuit with the input signal being not just limited to U of T signals.
So, one of the things, sorry. Basically your strategy when you got the Fourier version of the equation, you actually went through Laplace, but before transforming back to time from Laplace, you just transformed it from Laplace to Fourier.
Yeah.
And so, okay, and that actually seems easier than dealing with, because the capacitor, when it's in the Fourier, is 1 over JW.
Mhm.
So basically, instead of like going through that whole kind of algebraic, all those kind of algebraic moves with a fraction version of JW, you can just take your Laplace and just flip out S for JW.
Yep.
Okay.
Yeah, I like to use just S because it's, yeah, instead of S, instead of J omega, it's just easier looking algebraically.
Yeah.
So yes. Yes, there was some more questions, yes.
Just go over the integration thing again. Use which things cancel out and which things cancel.
Right here. Okay. So I had to write the Fourier, the inverse Fourier here for this term because it wasn't in the table, where the second term I was able to take from the table. So I put in the function, hopefully I wrote it correctly, and then you just multiply it by e to the j omega t. So it's f of w e j omega t, and then just 1 over 2 pi. So I just wrote the Laplace. And then I noted that it has the delta function in it. And so because it has the delta function, that will be, it will integrate to 1 for a delta function. But because it's also multiplied by e to the j omega t, and then the 3 plus j omega, this ends up actually going to 0. And so that term goes to 0, which makes it easy. And then I'm just left with the 5 times 10 to the minus 3 e to the minus 3t over 3t u of t. Does that clarify your question? Okay.
Yes, I guess my question was why would we need full transformation? Like why would we need the Fourier?
You could use, in this case, because the input signal is a u of t input signal, you can just use Laplace.
Is there a time where you need like full the same like problem with like why would that be?
So for part C of this, when we have the input signal is not a u of t input signal, you can't use Laplace. And then you would have to use Fourier. If you can use Laplace, typically it's easier to use Laplace. And then it's only like, I can't use Laplace, then I'm gonna probably go to Fourier. Yep.
Can you say that again one more time? The equation goes to y equals to 0. The integration part is 1 over 2 pi.
I don't have a great way of saying it. So let me come back to that one next time, but it does go to 0. It just mathematically works out to go to 0 when you do the u substitution. And so it's a little bit longer derivation. So I don't have like an easy answer. It just goes to 0 because I'm looking at this. You have to do, anyway, I'll come back to that next time to show that this is why exactly it goes to 0.
So Fourier is only easier if you simplify. Fourier is only for it. There's stuff happening before 0.
Yep.
Is the integral of any delta function is 0? Like any delta function times any amount.
No, it actually goes to 1. So it integrates to 1 for the delta function. But there's,
If you modulate it, it's gonna get the same.
and so it's because this is kind of a modulation that is why it goes to 0. But I don't have an easy answer to say why right now without deriving it more. So for now, trust me that it goes to 0. And next time I'll show you the proof of why it goes to 0.
So essentially, anytime we have like, so basically, the first thing is you did the integration on that part of some function because there wasn't anything in the table that translated it. So then the next step is it just because there's a delta omega in that integral that when you integrate it from negative infinity to infinity it goes to 0? Is that like kind of a safe understanding?
Yep, when it's this form, when you have delta omega times ej omega t over a plus j omega. So it's that combination is what gives you the 0. The pi is just a constant, and you treat j just like a constant also. So when you integrate a complex integral, you look at j as a constant number, pi as a constant number. So they all come out in 5 times 10 to the minus 3. So they all come out to the front. All right, other questions? Yes.
Make sure you got it. No, that's fine.
All right, so why don't you guys tackle the second input? So V of S is 10e to the minus 2t of t. Solve it both Fourier and Laplace. So the function will be the same, IC will be the same, it's just your input is now a different input.
Are we doing B or C?
B.
Okay, thank you.
So go ahead and try and solve this for an input of S of t equal to the 10e to minus 2t ut. Yes. Yeah, the quiz will be released today. So I put them both due Friday because I barely posted it Monday night late for the assessments to give you guys time to be able to work on those. So is on filters. What? Final. Let's see, so I'm trying to remember when reading day is. It's next Friday, so we won't have time to go through a review before the final. So final is optional. It will be retake options. If you want to do, then it will be 3 hours to the final exam time. So if you want to do all 3 exams, you would want to fit them into those 3 hours, or if you need additional time, I'd be willing to set up an additional time. So just let me know if anybody wants to take all 3 finals.
Are we gonna have like an assessment with the word Fourier transformation done all the time?
We won't know,
That'll be on the midterm.
but it will be on the midterm. So I'll put up some extra practice, like a,
Four questions total on the midterm. One for power transfer.
so I'll write those down, what they are. Midterm next Wednesday in Ingman.
Is it also possible to host like midterm 3 and final exam grades? I don't know.
Yeah, and I still haven't done exam 2. I realized I haven't posted a solution yet for that one, so I will make sure I get a solution up there. So it won't be possibly your own exam, but it will be, you know, some of the similar problems. So I will just post a solution. And if you have individual questions, feel free to let me know.
If we want to do like, Andrew said something about like, if we do the, like other assessments after it's like before it's grade or after it's grade, it creates difficulties for them or something like that.
Yeah, so I want to, but I haven't had time yet. I'll do some extra, like there'll be 0 points, but they'll be the same, like you can go through problems.
Just kind of practice.
Yep, just to have practice.
Okay.
So and I'll actually probably give you some extra credit for whoever wants to get credit who didn't get the assessments before. So it will probably be a little bit of credit if you want it.
Okay.
But yeah, I'll post some practice ones that you can just go through and have additional assessments to be able to work through. Let's see, okay, so AC power. I'm gonna copy it from this, let's see. So I'm going to go backwards now that I've written all this. So assessment and quiz both due this Friday night. So do make sure that they note that they're both due at the same time. So just make sure to complete them. Assessments are available. Quiz will be available today. And so just complete that by Friday night. So it will be filter questions. The quiz will be very similar to the assessment, where you'll have a circuit and have to derive the circuit equation and then graph it and determine what type of filter it is. And then there's also a possibility of asking about the frequency range of it, so the cutoff frequency. So that will be what you'll need to know for filters. And then for Fourier analysis, it's going to be more of what we're doing today, where you'll have a circuit and apply the Fourier transform to it, and then analyze it and transfer it back to the time domain. So it would be an input signal that you can't use Laplace for. So with that, we have not done a whole lot of practice with transforming Fourier from the time domain into the frequency domain and from the frequency into the time domain. So if I give you a function, it will be ones you'll already have seen, okay? Hopefully that will. So it would be what we just went through, or something similar to that, or something you can look at the table and move. So I just understand more concept, why you would use that. And then the mathematical portion, we haven't had a lot of time to work through. So I'll make it more like something you've already seen, or at least something you've seen. All right. Any questions on that? Okay. So for the exams, the online question was if any of the exams will be dropped. And so it will drop the lower, if you take a retake, it will drop which whenever is lower out of those two. So if you do take the retake and it ends up not being as good as your midterm during the semester, it will drop that one. If it is better, then it will drop the first one. Yep, so if you want to just come in and take one final, out of the 3 exams, you can just take one final. You don't have to take up. It's just an option up to 3. But because we are only having 3 hours, you would have to do each one within under an hour. And so depending on if you know yourself already, like I want to take all 3, but 3 hours is not going to be quite enough for me. I'm willing to also work and give another time frame. It'll probably take still a week to kind of get it graded. He'll try and do them as quick as possible. Yes.
So for instance, if I like want to load plot of the transfer function, for instance, like a best filter where it has a spike in the reflection and the cadences of like it increases. You have 3 points on there, plus or minus 3. Which one of those would be the competency? Like the actual, we have like the ideal. Like a high quality. Yeah.
Okay. No, I cannot draw. Backwards. Okay. So here, this would be if it was like at a 3 dB level, and then it goes 0 dB would be where you were measuring it. When you have a high Q, you are going to find that this point here, which is omega naught of this, will be the same as omega C. And so for that one, it would be at that location. If it's more ideal, you will be able to measure it well on the graph and be at, it will be right at 0 dB. But if you don't, and there is a high Q, you would be at that resonant omega naught value. So it would be the peak of that one.
Okay, that makes sense.
Is that more clear? I might have said that different last time. If I did, I apologize.
Does that matter if you're in DB, it's like
Mm-mm.
you just follow whatever the theoretical graph is?
Yep, so if this was, say, negative 3 dB instead, then this value would just be negative 6 dB.
So it doesn't really matter, it's all about just like the general shape of the graph.
Yep. So you're looking at the general shape. What shape is this? You know, in this case, it would be a low pass filter. And then to find omega C by measuring it on the graph, you would have either of those two situations where it would either be at the omega naught because it's got a lot of resonance and a high Q, or it would be able to be measured easily off the 3 dB less than it.
Would there be a question on the term of this not
It could be, yes. So do make sure that you are able to use MATLAB. Is that a barrier for you?
I was just asking, like, I need to bring that up.
Yeah, so we'll be on the computers, so you can do either the MATLAB that's on the computers in there, or if you want to bring your own laptop because you're familiar with the MATLAB on that, that's fine. But yeah, you will probably have to graph something on there at one point, just because that's the way I've asked you to do the filter.
You have to, like, take a picture of that.
I would put, yeah, I would do a screen grab and put it on your notes to upload. And your code that you use in MATLAB in case you write it wrong. The control toolbox, and then you may want also the symbolic toolbox, depending on if you want to use some of those functions or not. All right, we did not have a lot of time today, so I will complete these notes so that you guys can have these to compare to. Monday, we'll go over the third one on this, which is where you have to use Fourier only. But I do encourage you to use it as an exercise and then just compare that you're able to get the same answer. And online, there was a question that asked if we could have practice problems to reflect all 4 of these problem types. So I will also work on getting those available. Again, they'll be kind of extra credit instead of a full assessment or quiz value. So yes, Sam, I'll work on getting those available. All right, any other questions? All right, see you guys on Monday.
I just wanted to ask, I got all the way to here. Am I tracking correctly for VS and T?
So I see would be 20.
Oh, this is Fourier, not Laplace.
So it'd be 20 over 4K, which would be 5 times.
Wait, why isn't VS if it's 10 e to the negative 2t?
Yeah, this is the same. 20 over 4K is this.
Oh, okay.
Yeah,
Yeah,
it's the same.
okay.
Yeah, so
And
from
then-
here, you'll need to use partial fraction.
So it's method of, okay, so it's basically the same, so just method of partial fractions, nothing special about, so is the root found in relation, omega is the variable, right?
Uh-huh.
So J is the constant, so just treat, this is just a complex number times a variable.
Yeah, so
Okay.
all this means is that you have a 0 at the origin because you have a J omega term in there.
In there, okay,
So if you're looking at that imaginary real plane, you're just gonna add the 0. There'll be like a point right there.
okay,
And then you'll have these 2 poles
okay,
on
Awesome.
it. And that's all that those mean. And then the numbers end up working out. So you
Do you
leave,
have, do you have your result? And then I can
Yeah.
just, so IC of T equals 15 e to the negative 3t minus 10 e to the negative 2t. Oh, milliamps. So I got, yeah, actually I got the same thing. I just didn't put it in milliamps for Laplace.
okay,
So I guess that's a good point. I can double check my work.
They got the same.
yeah, they should
Yeah,
be the same. Those should be exactly the same.
Awesome.
Can I ask you a favor? Can you
Yeah.
upload videos of the Fourier exercise? Maybe to. Because
Yeah.
we didn't have time today.
Yeah. Yeah,
So
I'll,
we can-
I'll record the solution of this one and the next one.
Okay.
Is that, would that be
Yeah,
helpful?
yeah, it's just
Okay.
that we didn't have time, so.
Yeah,
cannot-
I
I mean,
will
I
record
don't have enough
those.
questions because I truly don't understand, but I just have questions about math, but not about Fourier transform, the
Okay,
circuit.
Yeah,
So probably if
Okay.
you,
I'll go through and record the videos of these and then also the next problem.
yeah, so we can have more questions one day, probably.
Yeah, so I'll
About-
also do this one
Okay, perfect.
and solve that one and record those. And then additionally, I'll have some extra practice problems.
Okay, thank you.
And then we can talk about it on Monday.
Thank you.
Uh-huh.
I think for this week's assessment.
Yes.
So I'm doing the MATLAB part.
Okay.
I'm getting it wrong. Maybe I'm not getting my graphs right. I'm just wondering why, because I'm still not